For those of you who are new, I'm a chemical engineer by training, have spent a lot of time on chemical process development, process scale-up, environmental and process safety activities, and volunteer to do this course because I think it's important that people don't get complacent with these major risks associated with a number of high-volume liquefied gases. And we're in the home stretch today. We've gone through 3 different segments so far, and according to the abstract, we are supposed to discuss ammonia and SO2. Now, I have 4 hours worth of material on ammonia alone, so we're going to not touch much on SO2 at all, and probably not at all today. And it's probably going to be next year's course. We'll do more on SO2 because most of the questions I get are on ammonia and very few on SO2. For those others, we've talked about propane and chlorine. Ammonia is a very large tonnage, 135 million tons per year globally, about 16 in the U.S., fluctuates up and down. In the U.S., we are going to be back in the business of producing more ammonia here in the States. And why is that? You want to volunteer the answer? Well, there's demand, but there's something else that has changed. Feed gas. Feed gas being methane, which is how you make ammonia. You use methane as one of the key materials. I am sorry. I thought I turned it on. So, one of the reasons we're going to start producing more ammonia in the United States is because we've got a lot more methane, which is a key ingredient. We have been importing a lot of ammonia into the U.S. from low-cost producers of natural gas offshore, where they essentially had stranded gas. They had no other way to get rid of it other than producing another product, and ammonia was a shippable product that could be shipped much more easily than liquefied natural gas. Ammonia has a number of characteristics, and I want to offer to you the advice I gave in the chlorine section. There are many industry associations that can provide a much better summary than I can of all of the properties of ammonia and their various gases. Here is one, anhydrous ammonia training tour by TransCare and the Fertilizer Institute. And I'll show a couple of clips. If you go online, look for TransCare, look for the American Chemistry Council, look for the Fertilizer Institute. They give training courses on emergency response, as well as have a lot of online information about how to handle the risks associated with ammonia. In this discussion of ammonia today, I'm going to talk about hazards. I'm going to talk about risk controls in transportation, and like in the case for propane, ammonia gets transported by a lot of different means and in a wide variety of quantities depending on the transportation mode. And then we're going to talk about risk controls for stationary use sites, and we're going to focus on, I'm going to talk about a lot of different ammonia uses, but we're going to focus on ammonia refrigeration because that is by and far the largest single user, and certainly in California. Commercial ammonia products, and we talked a little bit about in the last session about inherently safer approaches. So there is some confusion at times when people talk about ammonia and aqua ammonia. Ammonia is anhydrous ammonia, and aqua ammonia is ammonium hydroxide. Commercial grade anhydrous ammonia is actually not completely dry, but it's pretty close. But it does have certain level of moisture in it. Two common commercial grades of aqua ammonia are roughly 30% and a little under 20%. And There are great differences in the physical properties between anhydrous ammonia and aqua ammonia that have a very significant impact on the safety and use and safety and storage between the two. So if there is an opportunity to cost effectively, first it's got to be technically feasible, but then if it's cost effective to use to use aqua ammonia, ammonium hydroxide, there's some real safety advantages in terms of risk management to using aqua ammonia instead of anhydrous ammonia. Anhydrous ammonia has a boiling point about minus 28 degrees Fahrenheit. Vapor density, those of you who were at the previous sessions know that the easy rule of thumb is that the ratio of density of a gas to the density of air is the ratio of molecular weights. And the average molecular weight of air is about 29, close to 29. So that with ammonia at what? You got nitrogen, you got 3 hydrogens, 17. So what's it going to be? It's going to be lighter than air, right? It's going to be 0.6. You see the characteristics here. I'm not going to read all of them to you. What happens when ammonia reacts with water? This is the reason that ammonia is very hazardous. What do you have in mucous membranes in your eyes, your respiratory tract? You've got mostly water. When you inhale, when you come in contact with ammonia, it's converted to ammonium hydroxide, which is a very strong base, very damaging to tissue, causes blindness. Ammonia also will react, corrode copper and brass. There was a recent Ammonia Safety Day that was focused only on this subject of getting the brass out. So this is a big issue in ammonia systems or materials of construction and mechanical integrity to make certain the system stays as designed in terms of materials that are in use. Possible consequences, and again, you can get a lot of this information in much more detail off of the presentation that's offered by TransCare for ammonia emergency response. But due to its hygroscopic nature and the alkaline pH, it's extremely damaging to tissue. Also, liquefied ammonia can cause frostbite. I'm going to go back up to that. Minus 28 degrees Fahrenheit is not in the cryogenic temperature range, so it is not a cryogenic fluid, but it can still do a lot of tissue damage at that temperature. Let's talk about some of that damage. Fatal accident. And during the course of this presentation, I'm going to give examples, and I want to give a balanced approach. And I've tried to, and maybe I've forgotten to make this statement, I try to make this balanced. I'm not trying to overstate the risks associated with these hazards. These hazards are managed very well in the private sector with the help of some government oversight, with the help of consensus standards and good industry practices. But there is room for improvement. We're not perfect in managing these risks. And so I'm going to talk about incidents, and I'm doing this to make certain that people understand these are not theoretical events that could happen. These are things that have happened and unfortunately continue to happen, where people are killed, people are blinded by exposure to ammonia. And people are killed and harmed in other ways by exposure to other liquefied gases that have been discussed during the course of the day. So in this particular incident, which occurred in 2001 during the maintenance of a wipes surface heat exchanger that was cooled by liquid ammonia in a food processing plant, the estimated quantity of ammonia that was released was about 390 pounds. The total quantity of ammonia on site in this cooling system was 250,000 pounds. This was a big facility. Just out of curiosity, does anyone know what the largest facility in the U.S. has in terms of its inventory? At least the largest I know about. Is it about this? 10 times this? How much? No, it's about twice this one. It's 400 to 500,000 is the biggest ammonia refrigeration system I'm aware of, which I'll talk about in a little while. Now, in terms of one worker died due to massive skin and extensive airway burns due to exposure. The coroner commented that the employee who died had his airway swollen shut as a result of exposure to ammonia. It's a terrible way to die. A second employee also had significant exposure and was permanently blinded in both eyes. These kinds of things happen and the consequences are severe, not only on-site, but they can be off-site. The good news is when we get into talking about consequences, most of these events have on-site consequences, but not always. When I say on-site only. Now, human reaction to ammonia. The good news about ammonia, good news about a chlorine hazard as compared to some other things, are that they are detectable readily by smell. So with ammonia, you can typically smell it at 5 to 20 parts per million. 125 parts per million, it gets irritating. 300 parts per million is the IDLH, immediately dangerous to life and health. And as we talked before, doesn't mean you're going to die if you're exposed to 300 parts per million. It means that you're going to be very uncomfortable and you need to evacuate, you need to escape from the area. Once you get up to close to 1,000 parts per million, you're going to be extremely uncomfortable and unable to stay in an area. Once you get exposed to higher, when you start getting over a couple of thousand, you start moving into the lethal range, and typically at about 4,000 parts per million, it's lethal. Now, as I mentioned, that is 10 times an order of magnitude higher than for chlorine. So this is not as toxic as chlorine, but it is toxic. Now, in the last part of the session today, we're going to talk about consequence modeling and using things like Aloha models and looking at plume concentrations. And so within a plume from a release from an ammonia refrigeration system, we're talking about in-plume concentrations that could easily be in the 50 to 150,000 part per million range. So going into an ammonia release plume can be very dangerous to your health. And let's go back a little ways and talk about that number there on vapor density of 0.6. Now you see that number 0.6 relative to air. So you're going to say you're going to think that ammonia is going to go where? It's going to go up. Well, it will eventually. But as we talk in the consequence modeling, it's not going to at first. And it depends on how soon it's going to go up, where it's released, and the conditions for release, and what height, the pressure, the temperature, whether it's liquefied ammonia from an atmospheric storage tank or whether it is pressurized ammonia and where it is in the system. If it's on the hot side or cold side of the system, makes a big difference. How many of you are with regulatory agencies, either Cal, EPA, CUPA, etc.? Most of you. How many are you in the audience? How many are here from a user of ammonia for ammonia refrigeration? 1, 2. Okay. Was that a hand in the back? 3? No. Okay. Now, physical properties. One of the reasons why ammonia is so widely used is because of the fact that it can be liquefied at relatively low pressures, at room temperature. So if you look at a vapor pressure versus temperature curve, which I've shown on the left part of this slide, and you probably, and I know you can't read, but I've given some values there. So when you go by West Sacramento and look at those big, they're in Stockton, Port of Stockton, what are there in terms of ammonia? Does anyone know? There are some bullets, but there are also some atmospheric storage tanks, right? That have a lot of ammonia in them. And the big storage tanks operate at minus 28 degrees Fahrenheit. And why is that? Because it is much cheaper to store liquefied ammonia at atmospheric pressure in very large tonnage quantities. So those vessels are at minus 28 degrees Fahrenheit. Now, we're going to talk about Levees a little later, so remember what that temperature is that's in that vessel, and it is at its atmospheric boiling point. That's the answer to the question I'm going to be asking you. Now, if you look at this, as the temperature rises, 68 degrees Fahrenheit, the pressure of ammonia is 100 psi. G, 115 psi A, absolute. If it goes up to 100 degrees, the pressure is now 200 psi. And if it goes up to 115, it's 215. And if it goes up to 130, it's 315. Now, one of the things about liquefied gases is you never want to have a liquefied gas in a container or pipeline between two valves without pressure relief. And why is that? So let's talk about a scenario where I have on this side a tank truck with liquefied ammonia gas in it. And I've got a valve and I've got a hose connected to it. And over here I have connected this to another line where I'm filling a tank, and I've got a valve there. This is a bright sunny day in the Central Valley. And I've got that line filled now, that hose, rated at about 300 psi. And I close that valve in front of the tank, and I close the valve over here, and I go and have lunch. And the sun's beating down on that black rubber-coated, reinforced hose. And gets up to about 130 degrees, let's say, hypothetical scenario. What happens? Maybe nothing if you're lucky, but maybe not too. Maybe this happens. The hose ruptures. That's one of the things about designing liquefied gas systems, is that this temperature pressure, this vapor pressure curve is very important. Because while at room temperature the ammonia in this tank is at 100 psi, once it goes up to 130 degrees, it's over 300 psi. And if this tank's rated at 250, the pressure relief valve will have released if it's doing what it's supposed to do. This is why aqua ammonia, this is one of the reasons, has some advantages where it can be used. So when you look at the vapor pressure temperature curve for aqua ammonia, it's much different. So I've shown an arrow there going from 30 per 29.7, a very common concentration. So at 29.7% ammonia in water, the vapor pressure is what? It is less than 30 psi at 100 degrees F. Big difference. Big difference. Anhydrous ammonia would have a vapor pressure of 215 psi at 100 degrees F, or 7 times higher. And if you spill aqua ammonia, there's much less of a cloud of ammonia gas formed. So you have much less off-site consequences compared to anhydrous ammonia. It's still not pleasant to be around 30% aqua ammonia, believe me, but it's a lot less of a hazard. Now, Levees. the ratio of how much gas volume there is to liquid volume if you have a sudden expansion. So this is a rapid phase transfer. It's 850 to 1 for ammonia. So for every cubic foot of ammonia that you've got in that tank, you'll get 850 cubic feet of gas. And if that expansion happens very quickly, it's called a boiling liquid expanding vapor explosion. And those are extremely hazardous. And most people associate them, as I've hammered on everyone all day long, with propane and flammable gases. Levees can happen with any liquefied gas that is present in a container at a significant temperature above its boiling point. So, question for the exam. Those big tanks in West Sacramento and Stockton that are storing liquefied ammonia at minus 27, minus 28 degrees Fahrenheit, 1 atmosphere pressure. Can those tanks levee? No. No. The answer's been yes all day to the question, but this is a different question. And what's the difference? For a tank to levee, it has to be a liquefied gas, and it has to be at a significant level above its atmospheric pressure, the temperature significantly above its atmospheric boiling point. And that is not. So it will not levee. Now, if you've got a bullet tank sitting right next to that tank that's at 70 degrees Fahrenheit, can that levee? Absolutely. So the evaporation, 100 pounds of spilled liquid is about 20 gallons and could produce more than 2,000 cubic feet of ammonia vapor when it evaporates. One of the key properties that makes ammonia such a good refrigerant is a high latent heat of vaporization. Not as good as water, but it's good. 600 BTUs per pound. 6/10 of what it is for water. Has very good heat capacity too. But these small releases of ammonia from a refrigeration system, 1 pound of ammonia released can provide a significant volume to get up to a level where you could easily smell it. So you discharge 100 pounds of ammonia out of your ammonia refrigeration system, out of your storage tank for distribution to on-farm use, and you can contaminate a gas volume of 90 million cubic feet to a concentration of 25 parts per million. That's 100 feet of air depth over 4 city blocks. Now, will that 25 parts per million hurt anyone? No. 25 parts, it will not be something people will enjoy, but 25 parts per million is the acceptable level for exposure for long-term work environments. Now, let's talk about another physical property on ammonia. Ammonia has been considered as an alternative fuel, an alternative liquid fuel. I don't know how many people knew that. It's not a very good idea, in my opinion, because what you're doing is you have to get hydrogen from someplace, which typically comes from natural gas. Now, if you could generate the hydrogen from a nuclear power plant and then react it with nitrogen in the standard process, maybe you could make an argument, but I can't see that as being very cost effective. But the point I want to make is ammonia will burn. Ammonia is an explosion hazard, but it's much less so than for the fuel gases for a couple of good reasons. One is that, as I talked about, most hydrocarbon gases have lower and upper explosion limits in the range of 2 to up to maybe 13 or 14%. Ammonia's range is from 15% to almost 30%. Also, minimum ignition energy. Once you get a flammable mixture of a flammable gas such as methane, ethane, ethylene, propane, and so forth, the ignition energy is very low, 0.25 millijoules. The ignition energy to set off ammonia is 680 millijoules. This is the reason why in the fire code, and we'll talk about it, reference some of that, there are special provisions for not having certain electrical classifications and some options when you have ammonia and it's not treated as a flammable gas. The levee I mentioned. Now, let me talk about orders of magnitude in terms of presence of ammonia. And this just talks about how ammonia is synthesized, and we're going to be synthesizing. We already synthesize a lot of ammonia, but we're going to be running the existing ammonia plants at much higher on-stream times in the future because we're going to have much more natural gas. And where we get the hydrogen from is from the steam reforming of natural gas and the water gas shift reaction, which I show below. So we're going to be producing a lot more ammonia in the U.S. in the future than we have been for the last 20 years. Once we produce the ammonia, we have to transport it. Ammonia gets transported by many ways. It is a major item of commerce around the world and gets shipped by very large ocean-going vessels that go through under the Golden Gate. And on the west coast of the United States, there are 3 terminals. 2 of them are in California. One is the Port of Stockton, the other is the Port of West Sacramento, and the other is the Port of Portland, Oregon. They bring in huge amounts. The largest place in the United States for bringing in is the Port of Tampa, which has 3 very large terminals. So we'll talk about relative magnitude of the hazard in ammonia in a moment. It also gets transported by a number of other methods. Ammonia consumption, as I mentioned, was about 60 million metric tons per year. 70% of that gets converted to urea, 20% is directly applied. So if you go to some of these operations, like in West Sacramento, they will also be producing ammonium nitrate perhaps, or urea, which is a different form of getting the ammonia, the nitrogen into the soil. Only about 10% is used for other purposes. And for ammonia refrigeration system in a perfect world, once you fill it up, there's very little you ever have to do in terms of refilling it. Now, because of maintenance tasks and so forth and the need to purge the system for maintenance and so forth, you actually do have to fill it up. Top it off. I shouldn't say fill it up, top it off. Unfortunately, some people do have to fill it up because they have releases, but in most cases, they're just topping off. And I'll talk about some of these other uses. But in California, the big one is ammonia refrigeration. The other one is, listed here on the list, NOx control, catalytic reduction, selective catalytic reduction for NOx. And this just shows the green revolution. We have a green revolution because of not only good plant breeding practices and successes, but also because we've been using a lot more ammonia over the last 60 years globally. Now, to put things in perspective, in terms of large hazards, because many of you, and you know, so what's CalARP's lower threshold for ammonia refrigeration systems in the state of California? 500 or 5,000? 500. Okay, 500. What is it for outside of California? 10,000, right. Now, to put that in perspective, the port of the Tampa Bay port in Central Florida, what they do in Central Florida is they have major phosphate ore deposits. And the way phosphate gets delivered to the field is they convert those phosphate ore deposits to phosphoric acid. And then what do they do with the phosphoric acid? They neutralize it with ammonia to make ammonium phosphate. And so the port of Tampa Bay is one of the largest sites in the world for the import of anhydrous ammonia. So they have 3 facilities there, each close to 100 million pounds of storage capacity. So they have a combined storage capacity of 250 million pounds of anhydrous ammonia at any one time in the port of Tampa Bay. Big number, big hazard, big risk exposure. When we talk about relative risks and the magnitude of the hazards, you have to look at quantities. Large bulk storage terminals typically are 10 to the 8th, 100 million pounds. We talk about ammonia synthesis, often co-located with nitric acid plants. We're talking about 10 to the 7th to 10 to the 8th pounds, 10 to 100 million pounds. When we talk about large chemical plants converting ammonia to non-volatile fertilizers, we're talking about 10 to the 6th to 10 to the 7th. We talk about local distribution centers, small fertilizer plants. We're talking about 10 to the 3rd to 1 million pounds. The reason I'm making this point is this. As a society, as professionals in the chemical and mechanical engineering, electrical engineering, control systems, we have been able to do a very good job, for the most part, in controlling very large quantities of ammonia. So when you tell me that you have a system in California with 500 pounds of ammonia, what does that tell me? Does that tell me that's trivial? It does not. That is still a significant risk exposure, perhaps. But what it does tell me is that we have a lot of experience in handling many orders of magnitude. These aren't factors, these are orders of magnitude factors, orders of 10. So we've got a lot of experience to leverage off of to be able to manage ammonia risks very successfully. How is ammonia transported? Ammonia is transported across the U.S. by a number of means. There are a lot of import terminals, and historically the sources of cheap natural gas have been the Gulf Coast of the United States, where most of the ammonia production has occurred. It's also occurred along natural gas pipelines when natural gas prices were relatively low. There are numerous ammonia pipelines that are also connected to port terminals. So ammonia moves by pipeline, it moves by river barge, it moves by rail cars, as well as the big tankers that go into the ports on the Gulf Coast or into Tampa Bay or into the port of Portland, Oregon, or around West Sacramento. And it also gets moved by very small tanks, small tank trucks and small tanks called nurse tanks. And I'm going to talk about accidents that have happened at all the different levels across the supply chain. And I usually give this talk to people from all over the country, so it's not specific to California, but I'm going to try to pull out examples where I can for California. So let's talk about now some historical data on ammonia releases in the 15 states. During the period, a 5-year, 6-year period from 1993 to 1998, there was a paper published on the number of releases that appeared in the Journal of Occupational and Environmental Medicine in 2003, and I used this data when I was doing a risk assessment for one ammonia use system. And just wanted to try to get a feel for what the probabilities were in terms of failures of different systems. And so the bottom line is, let me just read a couple of these statistics. A total of 2,020 ammonia releases were reported in 15 states. A median amount of ammonia released was 200. 248 of these events, 12%, led to injuries to employees or first responders or the public. 12%. Not a big portion, right? 85% of the events with injuries were for injuries to employees or first responders only. 85%. Remember I said they tend to be on-site more than off-site. However, 50 to 60% of all injuries reported were to the public. Now, what were the extent of those injuries? In some cases, in very rare cases, those were fatalities. In many cases, those were reported because people went to the emergency room because they smelled ammonia, they knew they had been exposed, and it frightened them. They had very few symptoms other than they had smelled ammonia. Or they may have gotten a little short of breath because they were agitated, because they were upset that something may be happening to them that was not desirable. But the event was a non-event in terms of real physiological harm or damage. So some of these statistics, it's hard to read, but I'm not downplaying. I'm just telling you, those are the realities and the fact. Many of the injuries that are reported are because people smell the ammonia, not because there's actually any significant damage. Now, however, there were 13 fatalities reported. 8 were employees working at the sites, 4 first responder, 1 member of the public. So over that time period, 1 person, I could find data, had been killed off-site by an ammonia release. There had been more people killed by lightning. There had been many more people killed in automobile accidents and so forth. But that's not a good way to explain risk to the public. Of those 2,020 events, 88% were from fixed sources, non-transportation. 78% of the events occurred at fixed facilities, were attributed to equipment failures, and 12% to human error. I'm surprised that it's usually the reverse. Those equipment failures, though, were probably related to human errors and people not doing preventive maintenance on the schedule they should have, which is a management system failure, which is a failure of humans to manage the risk. 270 of these food industry events led to evacuations. Now, let's talk about some incidents. 2009, Louisville fire chief. Hazmat crew responded to the scene and determined there was an active anhydrous ammonia leak in a building. 2 seriously injured victims. The victims were identified. A gentleman by the name of Damon Shanks and Robert Corbin, 59. Coroner said both died due to exposure to anhydrous ammonia gas. This was a cold storage facility. The point I want to make is these events are infrequent, but they still happen, and they happen all too frequently based on that we should have learned from these events in the past. Poultry processing facility in 2009 in Lumber Bridge, North Carolina. Maintenance activity on a high-pressure refrigeration line. Release killed a mechanic, injured 6 other co-workers, caused the evacuation of the facility. 2010, 5 people hospitalized in intensive care because of an ammonia leak the day earlier in a frozen food plant. Because of these events, the leader of the Chemical Safety Board, Raphael Moore Iraso, stated, "We are seeing too many ammonia releases in our daily incident reviews. Though many are small, a high consequence accident that causes multiple injuries to members of the public is a serious one that warrants our examination." So there were 4 events that happened in rather rapid fire order. That one in 2009 with 2 fatalities in Louisville, the one in Lumber Bridge with 1 that I mentioned, the Tanner Industries in Swansea, South Carolina, where there was 1 fatality on a nearby highway, and the one that's in Rosemont, Minnesota, which I'm going to talk about in a minute. So let's talk first about this one in Swansea, South Carolina. I thought I had it next when I redid my slides, so we'll talk about it in a couple of minutes. Sorry. Now, in terms of hierarchy of control, I remember I stuck this in here to make a point. We talked about the ability to eliminate a hazard. And in the case where there is an option to use aqua ammonia instead of anhydrous ammonia, that may be viable from a technical and economic standpoint, and it would lower the potential, the level of the hazard and the overall risk. That falls under the category of eliminate or reduce the hazard, which is the first choice we always want to make. Then you design and implement engineering controls. Then you implement administrative controls, procedural controls that require actions by humans. Those are always somewhat suspect in terms of reliability. This is why we put in multiple layers of protection. We talked about that in some of the earlier sessions today. So, in the case of ammonia refrigeration, can we eliminate the hazard by eliminating the use of anhydrous ammonia? And the easy and short answer is no. And this is a statement made by the University of Wisconsin Industrial Refrigeration Consortium. This is another excellent group for information on ammonia refrigeration systems in terms of reliability. They put out a newsletter, which I get. It's great. You get it by email, and I'll give you a couple of examples. I've got one in here of one of the incidents they reported. But they've made it very clear. You know, this is one of the key facts is that you cannot eliminate ammonia if you want an ammonia refrigeration system. Managing the drawbacks, however, has enabled the continued use of ammonia in the industrial sector without having to eliminate the hazard. And I will go farther to say that we are going to, in the future, see much more ammonia refrigeration than we have in the past. So this is something we are going to have to live with and deal with, and we have the tools to do it. We need the operating discipline and management system approaches to be able to do it consistently and effectively. And I have great faith that we will do that. However, we still have looked at a lot of different candidates to replace ammonia. And out in what's very interesting, the space program, what did they decide to use for refrigerant gas? Ammonia. Ammonia is recognized as an acceptable refrigerant by the US EPA under the SNAP program, Significant New Alternatives Policy, to get rid of CFCs and HCFCs. Now, since I think everyone in here is familiar with why we're moving away from CFCs and HCFCs, I'm going to very quickly move through that part when we get there. Now, one of the other aspects of possible substitutions. Chemical transformations used to reduce hazards and risk are available for anhydrous ammonia. So you can use aqueous ammonia for the introduction of ammonia into the fields. You can also convert it to urea, or you can make ammonium nitrate. No good deed goes unpunished. Aren't there some problems with potentially getting ammonium nitrate into the hands of the wrong people? Very big risk exposure. But it solves a problem about releasing a toxic gas. Power plant stat gas NOx control. Remember I mentioned that while we call nitrogen an inert gas, nitrogen is truly not inert. Several slides back, I showed you a diagram that showed hydrogen reacting with nitrogen in a catalytic process to produce something called ammonia. So nitrogen's not inert, but it takes a lot of doing to get it to react. High temperature, high pressure conditions with a catalyst to react with hydrogen to produce ammonia. Where do we get NOx? High temperature conditions in the presence of oxygen and nitrogen gas reacts to form oxides. How do we produce a solution to that? We react it with ammonia in a process we called a catalytic conversion process, selective catalytic reduction. So there are various reporting requirements that I've listed here. 10,000 pounds, which you already know for at the federal level, 500 pounds for California, and general duty clause. Now, in terms of people managing the risks related to ammonia, and why they should do that even if they're below the number is, if you release ammonia, you're still subject to penalties under the general duty clause, because the general duty clause applies even if an RMP is not required, because it is the owner-operator responsibility to appropriately manage extremely hazardous substances, with penalties up to $37,500 per day. And has this ever been applied in California? Yes, and very recently. How many of you know about the South San Francisco event? In that event, Columbus Salami had a release from their system that was indicated the day of the release about 200 pounds. I just happened to be there in South San Francisco that day. I happened to be at the command center, and I happened to suggest, when I was told by the vice president of that company that the release had been about 100 pounds, I said to our guys standing right next to me, I said, just out of curiosity, why don't you run the Aloha model for 1,000 pounds and 2,000 pounds, just in case they underestimated the quantity. Later that day, I happened to be nearby when the tank truck pulled up and talked to the driver about how much ammonia had been put into the system to top off, and it was 1,850 pounds. Now, you could argue maybe the system was already low, but looking at the consequences and the vapor cloud and some of the effects, I think the number was closer to 2,000. But anyway, they got a $850,000 fine for not filing an appropriate and adequate hazardous materials business plan and risk management plan and doing an adequate hazard analysis. And they also have agreed to spend $6 million on a new refrigeration system. So, it is applied every now and then. There's an OSHA standard, as you know. There are a lot of other tools out there. As I mentioned, some of these. Now, I also mentioned today several times in the earlier section, I've listed it here again, risk-based process safety. There are also ANSI ASHRAE standards. There are trainings offered by RETA, the Refrigerating Engineers and Technicians Association. There are ammonia safety days. There are Ammonia Training Safety Institute, ASTI. There are various American National Standard safety requirements for storage and handling of ammonia. There are ammonia refrigeration piping handbook by IIAR. So there are a lot of tools out there that you can go to and that the folks in your jurisdictions can go to get advice and best practices. And I've shown on there also the Wisconsin group that gives a course every year on principles and practices of mechanical integrity for industrial refrigeration systems, which is where I sent engineers who worked for me to go to when we were evaluating installation of new refrigeration systems. These are areas where you can get a lot of good information, and as regulators, that may be a good place for someone in your organization to go as well, so that you have some of the latest information. Now, what is the expectation on owner-operators? The expectation by federal OSHA at least, and I cannot imagine that it is not the expectation of Cal EPA and Cal OSHA, the same, that companies will comply not only with regulations but with industry best practices. And some of these industry best practices, I'm not going to read the whole list, but there are a lot of them out there that are needed to run a system that handles anhydrous ammonia.
Hi, I'm Mike.
What I want to do is, I now remember what I was supposed to do. I want to show you a little bit of this.
Hi, I'm Mike Callan, and welcome to the TransCare Anhydrous Ammonia Tour. I'll be your host and guide for this training program. To give you a bit of my background, I was a career captain in the Wallingford, Connecticut Fire Department for 20 years, and have been responding to hazardous incidents and training emergency responders for almost 40 years, even before there were placards. I'm also the author of several hazardous materials emergency response guides and was part of the training development teams for serving propane and the pipeline industry. What I've learned from my experiences in order to respond safely and effectively to hazardous incidents, you need education, information, and support. One of the most valuable resources you have available to you is TransCare. TransCare is a voluntary national outreach effort that focuses on assisting communities to prepare for and respond to a possible hazardous materials transportation incident. TransCare members consist of voluntary representatives from chemical manufacturing, transportation, distribution, and emergency response industries, as well as the government. TransCare promotes safe transportation and handling of hazardous materials, educates and assists communities near major transportation routes about hazardous materials, and aids community emergency response planning for hazardous materials transportation incidents. Let's get started by telling you what we aim to accomplish with this training package. The overall goals of this program are to increase the responders' awareness and understanding of the risks and potential outcomes associated with an anhydrous ammonia incident, to increase your ability to recognize and identify the presence of ammonia in an emergency using current placards, labels, container shapes, tank construction, and other information, to increase your awareness in an emergency of the need for additional support and resources from railroad carriers, cargo transportation companies, and Chemtrec and Canutech, to provide basic knowledge of the hazards of anhydrous ammonia, its chemical and physical properties, and some primary risk assessment and basic terminology used in the ammonia industry. And finally, to provide some information on basic control and confinement operations within the capabilities of the resources and personal protective equipment provided by the responders organization found in your emergency plans. There is a lot of valuable information in this training package about anhydrous ammonia, including recognition and identification, chemical and physical properties, type of releases, life safety considerations, environmental impact, emergency response, and shipping containers. There are 4 units or blocks presented in this training program. Each block is delivered by a knowledgeable industry representative. I know many of these instructors personally, and they are well known for their expertise. The 4 anhydrous ammonia training blocks will cover anhydrous ammonia chemical properties and uses, transports and nurse tanks, railroad emergency response, and anhydrous ammonia emergency response considerations. This training package is primarily designed for first responders as a takeaway from a TransCare Anhydrous Ammonia Tour event.
Now, the reason I wanted to have you look at that is that this, again, just like the material from the Chlorine Institute, this is totally free. It is available online. You can download the material. You can send a request online to TransCare and get a CD. Several times a year in the state of California, they hold a training session, it's usually a half-day or a day session, on bulk transport of ammonia and ammonia's incident response and chlorine response. So if you have in your jurisdictions transportation of large quantities of ammonia or large ammonia storage facilities, this can be very useful and is a good resource which has a lot of excellent information from people who really know what they're talking about. So I would highly recommend, because I've gone to these as part of continuing education to just see how they're offering, and they're good courses. Now, they're not going to necessarily talk about root cause incidents, what I'm trying to get at here, but they're going to give you a lot of very useful information. So I would strongly encourage you to also investigate this. Now, in the second part of this, we're going to talk about transport accidents and transfer accidents. And I'm going to talk about where some of the events have happened and how they've happened in terms of containment vessel failures, valve failures, get into issues of transfer accidents from transport equipment for loading or unloading, and again, look at management system failures. And this is a slide that you already saw, just going over, and I'm going to walk through now some of these different approaches and talk about frequency as the first thing. So one of the things that will determine the risk exposure, in part, is the frequency something is done. It's also the quantity. So the mode of transport, ocean tankers transport quantities in tons per year of 5 to 6 million, approximately 500 deliveries per year would be expected. For barges, 1.5 to 2 million, greater than 650 deliveries per year of barges. With railroad tank cars, 4 million tons, and at the average quantity transported represents over 50,000 railroad tank car deliveries. Tank trucks, about 4 million. So compared to chlorine, we've got a lot more material moving by tank trucks with ammonia than we do in the case of chlorine. We've also, with both, we've got a lot of railroad tank car deliveries. And then nurse tanks, at 4 million tons, there are an awful lot of nurse tanks being used, filled and refilled after they've been emptied in the field. So in terms of looking at the potential loss of containment threat, the more times you have a transfer, the more opportunities you have for human failure, the more opportunities you have for layers of protection, engineering systems to not perform as required. So those are some things to consider. Now, the ocean tankers, where are all of those deliveries going? They're going to these big ports that I mentioned. On the Gulf Coast, primarily in Tampa Bay and over by in the area in Louisiana and Texas, and then on the West Coast, those 3 terminals. And when I talked about propane, ammonia and propane, LPG, liquefied petroleum gas, are often transported in the same ocean-going transport vessels. Now, when you think about the potential consequences of an event, when we do, for risk management plans, the scenario where we may lose the total contents of the ammonia storage tank and ammonia refrigeration system, which has 15 or 20,000 pounds, that's a lot less than this 250 million pounds that's in Tampa Bay. Or, on the West Coast, these are the numbers. Agrium, West Sacramento, is about 80 million. California Ammonia Company is about 80 million, and Simplot up in Portland is about 100 million. So these are very different scenarios. Now, let's talk about exactly how many transfers might be done. So let's look at Agrium in West Sacramento. They store from 30 to 120 million pounds. They've got various vessel sizes. They've got a large terminal. And why do we use this storage at atmospheric pressure? They would need 50 to 200 pressure vessels per site compared to 1 or 2 large atmospheric pressure refrigerated tanks. So from a risk management perspective, you've got a lot fewer vessels that's stored at atmospheric pressure. Yes, sir. With ammonia. Yeah. And so the vapor that comes off each of these ammonia refrigeration tanks are well insulated, but they're not perfectly insulated, so as the as the vapor rises, it's captured and put back into an ammonia refrigeration system. Bulk deliveries of anhydrous ammonia in the port of Stockton may equal or exceed 10,000 metric tons or 22 million pounds per delivery. How many, is anybody, what's Stockton, what county is Stockton in? San Joaquin. Anybody here from the Cooper from that county? No? Now, in transportation by pipeline, there are also a lot of pipelines that, that transfer material, and there was also the transport by barges and so forth, and those are regulated, as I mentioned earlier today, by DOT and the Coast Guard. And so I'm just going to flash over these. And let's talk about what's gone wrong in the past. And let's look at incidents. So released in 1976 as a Swedish ocean port during ship unloading of liquefied anhydrous ammonia. Now, the good news is I didn't find many incidents in the open literature for very large vessels. In this particular incident, over a period of 50 minutes, they lost 180 metric tons, 400,000 pounds was released, a lot of ammonia. 2 members of the ship's crew were found dead from exposure to ammonia. It was determined that the rubber hose used for propane and butane that was used for those and was not supposed to be used for ammonia. The inside of the hose had been partially destroyed, and this was the direct cause of the rupture in the transfer. So this was a transfer accident in transferring from the vessel to onshore storage. The pipeline industry, I'm going to talk about an accident that happened in Kansas. This incident happened in 2004. There was an 8-inch diameter anhydrous ammonia pipeline that ruptured. It was buried 3 to 4 feet underground. It was operating at close to 1,000 psi, ruptured near the town of Kingman, Kansas, but it ruptured in a rural area, in a farm area. 200,000 gallons, or about 1 million pounds of ammonia were released. And this shows the route of that particular pipeline. And it shows the place where it ruptured. No people were killed in this incident. Now, what contributed to the magnitude of this incident? Remember I mentioned that for those of you who were here, when we talked about propane and the Pemex disaster where over 600 people were killed outside of Mexico City in that disaster in the 80s. These folks had the same problem in terms of responding. They saw a change in the pressure on the line, and they had not drilled on that particular scenario. And so they didn't immediately shut down the line, kept pumping. And so the consequences would have been much less if the operators would have responded appropriately and turned off the pumping to reduce the pressure on the line and stop the flow. Land transport, DOT required. Anhydrous ammonia is regulated by DOT as a hazardous material.
I have a question.
Yes.
On that pipeline, do they segment off different locations in the pipeline where they can actually shut it off?
Yes.
Is that how it works?
Maybe not enough.
Right.
And more often in the future, as we all unfortunately know, at San Bruno, California, there weren't enough shutoffs, and they weren't done fast enough. And what's one of the reasons that pipelines don't get shut down fast enough? Well, that's part of it, but part of it is the push for keeping it online for moving the product.
Right.
One of the classic examples of failure to respond appropriately to shut down pipeline activities was Piper Alpha incident in the North Sea, disaster with OxyChem. They continued after Piper Alpha had the first release. Piper Alpha would have probably survived, and undoubtedly more of the people would have survived if the other platforms would have shut down production and stopped pumping oil and stop gas flowing to the platform. But they didn't. And why didn't they? They were worried about shutting down production. They didn't have the authority to shut down. So that's one of the lessons learned here, is to shut down more quickly and to make certain people are trained and understand what these pressure deviations mean. As I mentioned in one of the other classes, I was just at a very large facility, and this is becoming much more commonplace now in the process industries, is to challenge the operators with offline simulators to simulate emergency upset conditions. And this is becoming very standard in the process industries now, including the pipeline industry, so that operators know how to respond to upset conditions and even abnormal conditions that have not been addressed directly in operating procedures. So hopefully we're getting better at this, but we're still seeing these events. And why this pipeline, there's a long story, so I won't go into the details. They never really figured out why this pipeline failed, but it's probably because of lack of inspection during installation and some damage to the pipeline. Transportation. Ammonia is identified as a Division 2.3 toxic gas for international shipments, as a non-flammable gas for domestic shipments. Non-flammable. I told you ammonia can burn though, right? But that it's got an upper flammability limit, a lower flammability limit of close to 15% and upper of close to 30%. So it's not considered a flammable gas for domestic shipments. It's definitely considered an inhalation hazard. Risk controls for railway transport. I've already gone over this in terms of Levees, and just to emphasize, ammonia tanks can levee. It's not just propane. And some of these things that have been done to change the standards for pressure vessel design, for pressure relief and so forth, internal excess flow shutoff valves, tank head shielding to minimize tank head punctures, tank insulation to minimize heating during fire exposure, and these double shelf couplers so that you don't get so that when you have a derailment, that many more cars will derail, but you're not going to have the cars separate, because the separation of the cars can cause a lot of problems in terms of spearing adjacent cars carrying hazardous material. So it's considered to be the better choice to have these double shelf couplers that keep the couplings together so they can't move up and down, and so you won't have the cars uncoupled. And then you have to pull more cars back onto the rails. This is just some information. This is all information. These are pictures I took at this TransCare, one of these TransCare events. So you can get all of this information free of charge online, or you can go to the training courses twice a year in California, free of charge. This is what the top of these vessels. Now, I want to emphasize that point about, on this previous slide here, about the internal excess flow shutoff valves. Those are on these vessels. So if this tank, which has this protective housing around these top valves, if this tank is overturned during a derailment and this protective housing is damaged and sheared off and all of these valves are sheared off, there's another backup safeguard in there for these valves to automatically shut. Now, When you are withdrawing product, however, from these tanks, and if you have a restricted line flow, the line flow that's possible, the maximum flow, may be below the point where these valves will shut off, so that these valves will not do you any good in terms of shutting off the flow. And so that's the reason that auxiliary controls, another layer of protection, in addition to what's on the tank car, are often used. And they generally work, but not always. I've already talked about Levees, so I'm not going to talk about that more here. Now, let's talk about some specific incidents. So, we've had a lot of things happen in terms of better design since the Kingman, Arizona Levee with the propane tank. And we've got tanks that are much better able to survive incidents. So here's a situation in February of 2001 in Red Deer, Alberta, Canada. More than 70 metric tons of anhydrous ammonia was released from a railroad tank car that overturned. 34 people went to the hospital. One individual died while crossing the railroad right-of-way. Here's what can happen. Bottom and top shelf couplers. You can still see cars come away from one another. They decouple, and sometimes they will spear the other car. In Minot, North Dakota in 2002, an eastbound freight train traveling at 41 miles per hour derailed 31 of its 112 cars. Now, the reason I put that 41 miles per hour, and the reason that some of you who only came now, I'm going to tell you the information that was in the other section. Those tests that were done by the Department of Transportation to look at the effectiveness of the front and rear head shields on the tanks said they were effective at 19 to 20 miles per hour. This is 41 miles per hour. They are also only effective if the spearing is done where you've got that extra shielding. And as you can see on these tanks, what do you see? And some of those tanks are lying sideways and they've been T-boned. The penetration doesn't always occur where the shielding is. Now, this was a particularly serious event. 11,000, almost 12,000 people lived in the area. Only one president was fatally injured. 5 tank cars ruptured, releasing 146,700 gallons of ammonia initially, and another 74,000, over 1 million pounds of ammonia got released in this incident. It's lucky it was in Minot, North Dakota, which only had that population. It's very lucky that only 322 people sustained minor injuries and only 11 serious. Benson, Arizona, derailment. I wanted to show you this picture. This is a near miss, close call. What happened here? A string of 19 rail cars were involved in derailment. Mostly empty cars were not connected to a locomotive at the time. They were parked by a siding and started rolling downhill from a siding where they'd been stored. 2 of the derailed cars were each filled with 24,000 gallons, 120,000 pounds of ammonia. Does this remind you of the incident I mentioned where the car went for a joyride outside of Las Vegas for 20 miles before it was finally stopped because it was a runaway railroad tank car? The cars were traveling at an estimated 40 miles per hour when they hit an automatic derailment device. No anhydrous ammonia was released. Good design, as well as some luck. That when those cars piled together, that no one of them, it looks like, got the coupler spearing through the side of the vessel. Now let's talk about how things can go wrong, even for those companies, like in the case of the company that I described that did a lot of the right things with trying to manage their chlorine risk in terms of putting automatic shut-off devices, detection devices in place. So this is an incident that happened in France in 1994. This was a facility for unloading ammonia tank cars, and they had a sudden, unexpected, unjustified automatic disconnection of the liquid and vapor lines to the tank cars. And these automatic disconnections often would happen. The systems are put in place so that in case there's another rail car that comes along and bumps a car while it's being loaded or unloaded, that they will automatically disconnect and the shutoff valves will close immediately. And you'll lose some material that's in the line, but the spill will be relatively minor. So again, what kind of safeguard is this? You've lost containment, but you mitigate the measure by making certain it's a small amount. Now, what happened here? Failure of closure mechanism for the valves on the tank car. So they've got a great system in place. And so what did I tell you? There are 4 steps in risk management. You've got to know what your hazards are. You then got to know what the risks that those hazards present are. You have to assess those risks to see if they're tolerable and decide if you're going to put more controls in. You got to make certain you know what all those controls are, communicate, and then you've married those controls. You have to inspect, test, calibrate, and maintain to make certain that those controls, those risk management controls, perform on demand. And again, that's not what happened here. Consequences and some lessons learned. The result of this event was a release of 27 metric tons, almost 60,000 pounds, at an average rate of 1,500 pounds per minute. Fortunately, there were no serious injuries during a 4-hour response involving warning of the release and advisories to shelter in place. A serious accident is always possible even where there appears to be a sufficient number of redundant controls level of protection. Checks must be performed following maintenance, counting of parts. What happened here? Well, what happened here was that they had something left over after they did the maintenance. There was a bolt that somehow didn't get put back where it was supposed to that ended up in the shutoff valve, and the valve wouldn't shut off. Conduct of operations, operating discipline. Cargo tank trucks, they typically have over 3,500 gallons of capacity, and they're all DOT-rated vessels. So, what could go wrong here? They've got a lot of codes. 100% X-ray of all pressure welds is required. Stress relief per ASME code. Wet magnetic particle inspection. All sorts of standards have to be met. So, I talked about a levee, and I mentioned that there are mechanical damage to a vessel can cause a levee. So this is the example. National Transportation Safety Board report of an incident in Houston, Texas, 1976. The front end of the tank separated from the main body of the tank, and this permitted a sudden and rapid, complete release of the entire contents of the anhydrous ammonia vessel. The left side of the tank was scraped as the front of the tank was dragged along the outboard surface of the ramp. The driver took a turn too quickly on a ramp off the interstate highway, going on an overpass. The tank failure was probably initiated at the point on the shell to head weld where scrapes had reduced the thickness of the tank shell. The front head separated from the shell, and the escaping gas propelled the tractor cab into and around the column and onto the median of the roadway. After the front head separated, the forward and center transverse baffles were blown out of the tank. The remainder of the tank was propelled rear end first into a second ramp support column. This is a picture taken 5 minutes after the midday accident had happened at the intersection of Highway 610 and I-55 in Houston in the middle of the day on Tuesday, May 11th. The tank truck fell 15 feet onto I-59. The tank catastrophically failed. You know those scenarios that you have to do for CalARP with catastrophic failure of a vessel? And all of us say they can never happen? That's an overstatement. And probably maybe that's true for a stationary tank. But here's a catastrophic failure of a tank. The tank catastrophically failed and almost instantaneously released 38,000 pounds of anhydrous ammonia, blocking the freeway. Here's a dispersion model that shows the dispersion. I've shown the red zone, which represents the estimated boundary of greater than 10,000 parts per million. As I mentioned before, at more than 4,000 parts per million, that's a lethal concentration. The plume this plume stretched more than a half mile. By the way, that plume in Minot, North Dakota was miles long. It was 1,970 feet long, 1,150 feet wide. 6 people died, 5 from inhaling ammonia right on the freeway, trying to get out of the plume. Another 178 required medical attention. 78 of those were hospitalized with serious injuries. All victims were within 1,000 feet of the release and were outside of the vehicles, either trying to leave the area or to help others. Fatalities and serious injuries occurred within 230 feet of the release point. The blue zone represents a zone with greater than 1,200 parts per million. So when we get into consequence modeling, how many of you have used Aloha models as part of your activities? They're not perfect, but they're very useful to help in consequence analysis. What else can happen in terms of causing a levee or leak? And not all leaks will become levees. So this is an example of an incident that happened in Middleton, Ohio in 2003. AmeriGas, an MC331 tank, manufactured in 1977. The front head failed from intergranular fracture in the carbon steel and began to leak. Failure was deemed to be typical of stress, corrosion, cracking, and caused by hauling ammonia with too low a water content below the 0.2 authorized per Title 49. So remember I said anhydrous ammonia is not completely anhydrous. There's a reason for that. Complying with standards is important. Luckily, this wasn't a catastrophic failure. Ammonia terminals. This doesn't apply to us in California because we don't have river terminals or pipeline terminals. These terminals store very large quantities of ammonia under low temperature conditions in most cases, although they also have on-site bullet tanks. This particular facility in Minnesota had 2 refrigerated tanks with a storage capacity of 60,000 tons or 120 million pounds. And they also had a bullet tank. The site was the scene of a fatal accident. Again, a tank transfer. A 31-year-old truck driver was involved in truck filling, and they had a misconnection and failure, leak of anhydrous ammonia. Flow was stopped, but someone was killed. This is another unfortunate incident. This one happened in 2009. This is someone driving down the highway going to work. This again is ammonia storage facility like we have in California, like we use to fill tanks for distribution. At this particular facility, they had an ammonia release, and Miss Ginyard, whose picture is shown here on the left, died, and more than a half dozen other people were treated at a hospital. 7,000 pounds of anhydrous ammonia leaked out of a tanker truck in South Carolina when the tanker truck was unloading anhydrous ammonia at an ammonia distribution facility, probably for anhydrous ammonia for agricultural use or for ammonia refrigeration systems. She was going to work. She drove into the cloud. Her car probably stalled. She got out of the car. An ammonia cloud can have concentrations of between 10 and 100,000 parts per million, lethal concentrations. She didn't make it out of that cloud. Nurse tanks. There are a lot of them around. Do they ever fail? Unfortunately, yes. There's a picture I took out of the window when I was in Illinois out of a train, riding on the train. Just happened to see a lot of them at one field. Representative of the Fertilizer Institute has estimated that in 2004, there were probably 200,000 nurse tanks across the United States. Those tanks delivered about 4 million short tons of ammonia. That's a lot of different transfers every year. Here are the kinds of quantities of ammonia that's stored in these distribution facilities in California, some probably within your jurisdictions. Anywhere from 50,000 to almost 400,000 pounds. These nurse tanks typically have anywhere from 1,000 to 1,500 gallons capacity. I'll let you look at these slides at your leisure. You can see the different features in terms of how they're set up and the different safety controls and valves and color coding and so forth. And by the way, this is typically also included in some of these TransCare trainings. They'll also provide training on how to respond to and understand how nurse tanks are set up in the valving and how first responders can respond to mitigate the incident. So I'm going to skip over some of that and get to a failure. This happens to be a failure that occurred at a co-op in Iowa in 2003. You can see the underside of the tank, the weld failure with it, the weld essentially unzipped. This was a cooperative. They had 600 nurse tanks in their inventory, and they were filling this particular unit. The National Transportation Safety Board determined that the probable cause of the sudden failure was inadequate welding and insufficient radiographic inspection during the tank's manufacture and lack of periodic testing during its operating life, service life. Both nurse tank loaders suffered chemical burns over more than 50% of their body. Eye injuries, airways. The loader who had been on the loading platform when the tank fracture occurred died as a result of inhalation injuries. Here's another one, 2005. Prior to the failure event, an employee filled the subject nurse tank to 85% capacity. After the tank was filled, it remained at the filling station dock and the employee vacated the yard, luckily. This was a Levee. The tank failure and release of all contents was reported. They discovered a ruptured 1,000-gallon anhydrous ammonia nurse tank that was in two pieces. A portion of the rear head was lying near the filling dock. The remainder of the tank was approximately 100 yards away. No employees or customers were at the site. No fatalities occurred. Lucky. So, those are some examples of what can happen in this supply chain in terms of transportation. So let's keep going down. We're getting near the end. Now I'm going to talk about ammonia refrigeration. I'm going to quickly go over some different options here. One of the risk-benefit trade-offs that is often made where you can use anhydrous, when you can use aqua ammonia versus anhydrous, is in the selective catalytic reduction for NOx control and combined cycle power plants where you're firing with natural gas. And then you inject ammonia. As you see the chemical reaction there, you use ammonia that can react then with the NO and additional air, oxygen in the air to go back to nitrogen, or NO2 will react with ammonia to produce nitrogen. And this has been very successfully implemented. You can also use urea, and here are some examples in California of selected catalytic reduction facilities for NOx control. And you see quite a few of those that have anhydrous ammonia, but you also see I've put in here some examples from other parts of other locations around the U.S. where they have up to 400 to 500,000 pounds of anhydrous ammonia in inventory at these first two plants in Alabama, at this plant in Georgia. Well, a couple of them, they have 2 and 3 million pounds at these very large coal-fired plants. And pulp and paper, I'm just going to flash through these because these are not really relatively important for most of us in California. Potable water treatment, we also use ammonia, and it's being replaced more frequently by aqua ammonia, and this is used for dechlorination, or for chlorination, I should say. Ammonia reacts with the chlorine species to form chloramines that are more chemically stable. Anhydrous or aqua ammonia may be used, and that's one of the ways to make it inherently safer is to go to the aqua ammonia. Semiconductor use, there's also and light-emitting diodes, just a couple things that might be in your jurisdiction. In terms of light-emitting diodes, the inventory of ammonia is actually fairly large, over 100,000 pounds at one of the facilities in San Jose. Refrigeration. I'm going to flash through and let's just talk about it. Refrigeration systems have a real good history. One of the oldest facilities in the world is, in terms of ammonia refrigeration in a major metropolitan area, is the one at the Carlsberg Brewery in Copenhagen. They have a system containing over 150,000 pounds of ammonia, and they've had that in their inventory for the last 50 years in a population center over 1 million people with almost no incidence of any significant releases. A lot of good engineering controls. The point I want to make is these systems can be made to work very reliably for long periods of time if you have good engineering practices and good management system practices. This is some information on quantities that are used per ton of refrigeration. I'm going to jump ahead and talk about some of the issues around refrigeration systems and conditions inside a system. When you're looking at ammonia refrigeration systems and vapor compression type refrigeration systems, you've got the high pressure side and the low pressure side and the high temperature and low temperature side. And I'm going to jump forward even farther because this is the part I said I would skip about why we're using ammonia. And these are some of the quantities. We've got in ammonia refrigeration systems in California, most of the systems are typically in the range, and I've got it in the appendix, they're from 10,000 to 150,000, 200,000 pounds. There are systems around the United States, though, that are in the range of 300 to 500,000 pounds. And again, for the most part, they operate very well. There were some issues with Miller Coors, which happens to have the largest system in 2010, where they released about 2,000 pounds. These releases tend to be much less than in the transportation area. There are a lot of controls that minimize the release, but 2,000 pounds of release into a building is still a big deal in terms of potential worker exposure. Now, the high pressure side and the low pressure side, where the ammonia gets released in terms of consequence analysis, and we're not going to have time today to go through all of that, and I'm going to put the slides in, but that determines what actually might happen in terms of the plume. And when you look at a lot of outdoor systems where they have the high pressure receiver, this happens to be a picture I took from out onto the street of Growers Ice Company in Salinas. They've got about 140,000 pounds. And you see there the big tank, the bullet tank in the middle of the system there. That's the high pressure receiver, and they've got the evaporative condensers. If a leak occurs on the high pressure side, the conditions are going to be different than if you have a release on the cold side where you've got a cold liquid. And the response is going to be, in terms of the consequences and how you respond, might be different. And I'm going to fly fast forward through some of these. Let's talk about some of the releases, what some of the scenarios are and how releases occur. One of the things that has been done in many cases is to take the ammonia, is to distribute and circulate the ammonia instead of through the building on the rooftops, over the roof on external piping. Now this is good for potential worker exposure, but then you've got a release that would be outside. Now there are two ways to get away from this. You can also use dual fluid systems. And I've got a lot of information which you can read in here, and I reference various reports. Now, what can happen on some of these systems on the rooftop? Well, one of the things that happens with refrigeration systems is that sometimes you can have hydraulic shock. And this is a system, and this is a report that came out of the cold front, and this is a newsletter that you can get free online from the University of Wisconsin through the Industrial Refrigeration Consortium, and they show a picture of that. I show those two arrows, and the pipe in the middle, that is a catastrophic failure of a line on a rooftop from a hydraulic, essentially like a water hammer, a hydraulic hammer. This is a 6-month-old system where they had a catastrophic failure of the welds and an ammonia release. Many codes and standards that hopefully prevent those kinds of weaknesses in welds, and also operating procedures that will prevent those hydraulic shocks from occurring. And I've got a lot of information here that we're not going to be able to go over. Now, so one of the things you can do to reduce the hazards is to go to dual fluid systems. Dual fluid systems are being used much more in non-food refrigeration plants, but they're also being tested and demonstrated. And there's one in California, maybe a second's also been demonstrated, where you use ammonia as the basic system for doing the refrigeration. You have a secondary loop, and the secondary loop can use a brine solution. It can use CO2, depending on the refrigeration demand. And the reason I'm pointing out these dual fluid systems is we are going to see more ammonia refrigeration systems used in non-food and non-industrial applications. And I'm going to fast forward again and show this system happens to be in the middle of Stanford University. This is an ammonia refrigeration system, and they have a secondary loop. And so the entire ammonia refrigeration system is within the machinery room. No ammonia leaves the machinery room. And so if they have an event, I've shown the scrubbers on the roof. If they have a release, all of the ammonia is exhausted through the rooftop scrubbers and is scrubbed to well below the IDLH values. And with dissipation will be well below acceptable exposure limits if the scrubbers work. So they've got to have a good mechanical integrity program, and I hope they do. Yes? It's for circulating chilled water for building air conditioning, campus-wide system. It's a district cooling and heating system they have essentially. And I'm going to fast forward again. By the way, this is what happens when you take a liquefied gas and expose it to high temperature. They were doing maintenance on an ammonia refrigeration system in a synthetic rubber facility. This was an incident in 2008. And they shut off the pressure relief system, probably to change out the valves, and they had ammonia in the system still. And they put steam on the unit. Probably got up to, this vessel was code rated at probably 250, 300 psi. Based on the temperature, it probably didn't fail until it got up to 900 or 1,000. Mechanical engineers do a pretty good job with design, but not that good. And unfortunately, someone was killed. The question is, why are they switching from Freon to ammonia? Because of ozone layer depletion. It's been mandated. We have to move away from Freon-based refrigerants, halogenated refrigerants, and many companies have decided that they're going to do that. And let's talk about where we have major refrigerants. So this is a system in Fresno. It's a dual fluid system. You can read about that. And in urban areas, how many of you think we've got ammonia refrigeration systems now in major urban areas? We do. Somebody knows it. Let's look at a couple. Heathrow Airport in London just put in a major ammonia refrigeration system. Again, a dual fluid system. So the machine room is isolated, has controls if there's a release, and also these systems require a lot lower ammonia refrigeration ammonia inventory because you've got a secondary heat transfer fluid being circulated. Throughout many other parts of the world, including Chicago's McCormick Place, they also have an ammonia refrigeration system, which I've visited and talked to them about. Very nice system with controls right near the loop in Chicago, with an inventory of 30,000 pounds of ammonia.
Aren't those less efficient than just the single loop?
But much safer.
Yeah.
You never put in an urban area a single fluid system. Throughout much of Europe, here's a rooftop mounted unit right in the middle of London. We're going to see more ammonia refrigeration systems. You are going to see more ammonia refrigeration systems in your jurisdictions over the next 20 to 30 years in commercial and industrial applications, including conversion in Canada. There's a major activity underway and across Europe to convert from Freon-based refrigeration systems to ammonia refrigeration systems for ice skating rinks and major ice skating arenas. So, we are at the end of our time. I only have another 2 or 3 hours to talk, but I'm going to cut it off. You'll see the slides when I post them. There's some ones on consequence analysis and using the Aloha model. And you've got my email address if you've got questions. I hope you learned something. Please contact, for more information on aqua ammonia, organizations like this. Go back and look at the Coupa presentations. There are a lot of presentations that have excellent material, and keep managing those risks well. Right. Thank you.